Hi, Algebra 2. Today we move on to section 6.3, where we're going to start talking about these things called logarithms. You can see that the objective for the whole section is that I can evaluate and simplify logarithms. The first day of 6.3, we are going to focus on understanding logarithms, converting between exponential and logarithmic form, and evaluating logarithms. In order to start, we're going to make some connections. In this problem, you can see that earthquakes make seismic waves through the ground. The equation y equals 10 to the x relates the height or amplitude in microns of a seismic wave y, and the power or magnitude x of the ground shaking it can cause. Taylor and Chen used different methods to find the magnitude of the earthquake with amplitude 5,500. Okay, so we can first see in this table on the right-hand side that if an earthquake has magnitude 2, it has an amplitude of 100. Again, that's because we're using this equation, 10 to the second power equals 100. This one's 10 to the third power equals 1,000, so on and so forth. The problem came with 5,500 is that 10 to what power is 5,500? It's not a nice, neat number like the others. So let's look at what Taylor and Chen did. Taylor said that since 5,500 is halfway between 1,000 and 10,000, okay, so between this one and this one, it's about halfway between, or it is halfway between. He argues that 3.5 is halfway between the 3 and the 4, so therefore he's going to conclude that it's about 3.5. Okay, that sounds like good reasoning to me. Chen, on the right-hand side, he started to work it out, and he also recognized that it's somewhere between 10 to the third and 10 to the fourth, but you can see then he started using guess and check. He said, okay, 10 to the 3.5, that's 3,162, so he went up to 3.7, up to 3.8. Well, he realized then that it's somewhere between 3.7 and 3.8, and so through this guess and check model, he got that it's about 3.74. Okay, so he used more of a guess and check. Now, we're going to critique Taylor and Chen's work before we answer the other question. Okay, it says, is each method valid? I would say yes, they're both very valid. Okay, what are the downsides of both? Well, for Taylor, his is not as precise. Okay, so he had a very good argument for about what it is, but it's not super precise because he just went with the halfway mark. Chen's is probably a little more accurate. Having said that, he's guessing and checking, which isn't always the most efficient method. So let's look at this. It says, what is the magnitude of an earthquake with an amplitude of 100,000? We should have done that first, but remember, then we're saying 10 to what power is 100,000? Oops. Which again, because it's a nice, neat number, I can conclude that this would be 5. So here's the problem. We actually want to be able to solve 10 to what power is 5,500. That's really what this question is asking us to do, right? So far, we don't have the strategy to be able to do that, but that's what we're learning in this chapter. Our best method would be to solve that algebraically. The problem is I just need a new method to be able to do that, and that's what logarithms are all about. Okay, so here we go. Let's understand some logarithms. First, let's talk about just solving a very basic equation, 2 times x to the 8. And hopefully if I ask you to solve 2 times x to the 8, you're thinking, well, I would divide both sides by 2. Now, we probably don't usually think about it this deeply, but you do think about it at a basic level. And that is whenever you're solving equations, when you move something to the other side, you're undoing the operation. Meaning in this case, I have 2 times. So when I'm going to say multiplication. To undo multiplication, I divide. Okay? Now, having said that, this is actually using an inverse. So when we solve equations the way we always have, you're actually using inverses. Just like when we would usually have something x plus something, we move it to the other side by doing x minus. That's the inverse. Addition and subtraction are inverses of each other. Here's where we run into a problem, though. This problem is similar to what we just did. We have 2 to the x equals 8. Yes, I can ask myself, what times itself? So we read this, 2 to what power is 8? Okay, in last chapter we talked about what times itself 3 times, or what times itself, 2 times itself, how many times is 8? Sorry about that. 2 times itself, how many times is 8? Well, we know that that's just 3, okay? 2 times 2 is 4, times 2 is 3. So yes, in this case, I can say I know 2 to the third is 8, so therefore my x is 3. Here is the new thing we're going to learn. When we have 2 to the x equals 8, that's exponential form. If we want to use this whole idea that technically when we solve equations, we use the inverses or the inverse, you can switch it to logarithmic form because these are inverses of each other. So the first thing we have to know is how do we rewrite that? Well, if we want to write this in what we usually call log form, it would be log, and logs have bases. The base of the exponent, remember this was called the base of the exponential form, the base of the exponential form becomes the base of the log form. Okay, log base 2 of 8. Okay, the answer goes here equals the exponent. Because again, when we solve, we want to get the variable by itself. In this case, the variable is the exponent. So to get the variable by itself, we take the inverse, and that is log base 2 of 8. Now, one thing I learned a few years ago when we were piloting a different curriculum is that this other curriculum called the log function, the what power function. Okay, so this language that we talk about up here, when we read this log, it's called log base 2 of 8. That's how you would say it in words. But in terms of when we get to wanting to solve this, you're actually reading it, the log you replace with what power of, and then the base, so of 2 is whatever number is next to it. And if I ask myself what power of 2 is 8, I would write it like that, and so we get 3 again. Okay, so the log can be read as the what power function. I'd never seen that until we piloted a different curriculum, and I kind of liked it, so I wanted to pass it on. But exponentials and logs are inverses of each other. And therefore, it is going to be the scale or the strategy that allows us to start solving for exponents. Okay, so this is kind of a summary of what we just talked about. So the logarithm base b of x is defined as below. So log base b of x equals y if and only if b to the y equals x. Again, the b, these are both called bases. Whether it's in exponential or log form, that's called the base. But notice that the x and the y switch, which is again what we talked about doing with inverses. So the logarithmic function log base b of x is the inverse of the exponential function y equals b to the x. Okay, so let's try it. Okay, so all I want you to do is to write the log form of y equals 8 to the x. Hopefully what you got is log base 8 of y equals x. Okay, so log form, log base 8 of y equals x. Okay, so the base becomes the base down here, and then the exponent is by itself. That's kind of how I remember. Different teachers have different strategies to help you understand the conversion. So your teacher might have some other suggestions as well. Okay, so exponential and logarithmic form. Exponential form shows that a base raised to an exponent equals the result. Logarithmic form shows that the log of the result with the given base equals the exponent. So again, just another fancy way to show the exact same thing. This is the conversion, different letters. You probably already wrote it down, but when written in logarithmic form, the number that was the result of the exponential is often called the argument. You don't really need to know that, but it's good to know some language. All right, so again, really right now what we want to be doing is being able to convert back and forth. So in this case, it's asking for the logarithmic form given exponential. Okay, so we have to be able to go both ways. So I'm given the exponential, which means I need log. So I go log base, my base is 3, of the answer, 81. And that's going to equal the exponent, which is 4. And again, remember for me, I read this, it is the log base 3 of 81 equals 4. But if I was going to solve it, which we'll do in a second, and I just had the log part, I would say what power, that's what I replace log with, of 3 is 81. Okay, so that's a way we can think about logs. All right, in the bottom one, I want you to think about how would you take log form and switch it to exponential. Okay, so that's where you want to take it to the power. Well, again, the base, the 10, that stays as the base, but now the answer becomes the exponent. So 10 to the third power equals 1,000. So that's how I'd write that in exponential form. Go ahead and pause the video. I want you to try this one on your own. You're going to just convert both of them again. Hopefully, for your first one, you got log base 7 of 343 equals 3. Again, you could think about this as what power of 7 is 343. Okay, and the answer is 3. Now we took exponential, or we took log form and converted it to exponential. You should have had the base 4 to the answer, so 4 to the second power equals 16. All right, so that is the converting. Okay, we have to be able to go both directions. But now let's see why we would need that. Okay, because ultimately we want to be able to evaluate logarithms. Okay, so if they give me everything on one side, these are all things that I can actually solve by hand without a calculator. And again, this is why I like to think about it as the what power. As soon as I see log with all of this, I now read it as what power of 5, because that's the base, is 125. You don't have to write that down, obviously, but if I think about that, really it makes me convert it to exponential, which is kind of what we thought of last chapter. Basically, 5 times itself, how many times is 125? And I know that's going to be 3. So my answer for this is 3. I can answer that without a calculator. Okay, now sometimes we're throwing some different twists and turns. Let's look at letter B. Log base 1/4 of 16. Again, if I think about this, I'd say what power of 1/4 is 16? If I had a situation where I had 4 to what power is 16, that would be easy for me. I know that's 2. But once I have this fraction, that confuses me a little bit until I think about the rules we learned with exponents. Do you guys remember talking about negative exponents? What if I put a -2 in here? Because I know 2 is important, right? If I put a -2 in there, we learned last chapter, or reviewed last chapter, that we could distribute that. So I'd get 1 to the -2, 4 to the -2. And hopefully you remember, or at least it rings a bell now that I'm reminding you, as soon as you have negative exponents, we make those positive by flipping the piece over the fraction. So 1 to the -2 actually goes to the bottom of the fraction as 1 to the +2, and 4 to the -2 would move to the top of the fraction as 4 to the +2. So this actually equals 4 squared, which is 16. Here's the trick. Anytime you have a fraction as a 1 over something, and you have to get it equal to a number that's not a fraction, your answer is most likely going to be negative. So it's -2. Okay, next one, log base 3 of 0. Okay, so I'm saying what power of 3 is 0? Can I multiply 3 by itself and ever end up with 0? No way, that makes no sense. Okay, I can't do this. You're going to end up with log problems that you can't do. Those answers will be undefined. It's not possible. Okay, and in math, if it's not possible, it's undefined. Okay, now here's the reality. Anytime you're taking the log of 0, you're going to have some number to a power should equal 0. That's never possible. So just a little side note, anytime you try to take the log of 0, it's always going to be undefined. But we don't have to memorize that because we can just try to work it out and realize that it's not possible. All right, last but not least, sometimes you see it in a little different notation like we see here, log base 2 of 2 to the 8th. Well, I would say what power of 2 is 2 to the 8th? So while it looks a little bit scary at first, when I write it out this way, I'm like, well, for those two sides to be equal, this box for sure has to be an 8 because then the sides are identical. So that's 8. Another property or rule, if we wanted to try to memorize things, is that anytime the base matches this number, the answer is always going to be your exponent. But we don't have to remember that. We don't have to memorize it. We can just write it out using the what power idea, and we can see clearly that, of course, it's going to be 8. Okay, take another minute, pause the video, and try these 3 on your own to firm up these concepts we just got introduced to. All right, letter A. When I went to write 3 to what power is 1 over 81, I still have that 1 over something, but this time the fraction is the answer, but the same rule applies. I know that 3 to the 3rd power is 81. Nope, that's not true. 3 to the 4th power is 81. Sorry. Okay. So 3 times itself 4 times is 81. But if I do 3 to the 4th, it would be just regular 81. If I do -4, that is when it is going to be a 1 over -1 because it flips it. Okay, so again, whether the 1 over is the base of the exponent or if the 1 over is the answer, you're still using that idea of negative exponents. All right, the next one, similar to something we talked about, but different. 7 to what power is -7? Now, I'm guessing some of you accidentally put -1 as your answer. You mistook it for multiplication. Remember, we're actually saying 7 to what power is -7? 7 times itself, how many times gives me -7? That can't happen. Okay, can't do it. So this is another situation that is undefined. Okay, so we can't take logs of negatives either. All right, last but not least, what power of 5 is 5 to the 9th? Well, for these two things to be the exact same, that box has to be 9. So this is another case where the base and this number are the same, so the answer is actually the exponent. Okay, so that was our lesson for today. Just an introduction to logs. It is the inverse of the exponential function, and it's going to give us a strategy to solve for exponents, which is another layer of solving algebraically. Go ahead and work on your 6-3 day 1 Pearson practice, and we'll see you back here tomorrow to finish up 6-3.